This is section 4.6 of calculus. This is on related rates. Here's what we're going to see in this section. We'll start with related rate equations. We'll find a solution strategy, and then later we'll simulate related motion. So in this video, we're going to look more specifically at related rate equations. And let's begin this way. Suppose that a particle, a point, x comma y is moving along a curve C in the plane so that its coordinates x and y are differentiable functions of time. Let's pause there for a moment, and I have a Desmos graph for everybody on the next page. Here we are. So here's a curve, the purple dashed line, and we're going to call that the curve C that we referenced in the notes. And then the blue dot here at 0, 1, that's going to be the point x comma y. I've got it over here on the left as a comma b. And then I'm going to move a t, a time, from time equals 1 along the curve until time equals 10. And I want you to take a look at this point moving along the curve. Notice that it starts out kind of quick. And as we move further along, the point sort of seems to slow down. So this is a point that is moving both its x and y coordinates in relationship to time. The way we want to think about this is that both x and y, those coordinates, are not independent variables. They are dependent upon a variable t, time. So let's go back to the notes. If d is the distance from the origin to P, so if we drew a line segment from 0, 0 to that point, then using the chain rule, we can find an equation that relates. Ooh, what is this? d dt, dx dt, and dy dt. Those are rates of change with respect to time. So let's take a look at that on the Desmos graph. So if we put in that segment and then watched that segment change again, there's the line segment. It's in black. It stretches from the origin 0, 0 to the point, the blue dot, a comma b. In our case, it's x, y from the notes. And notice that again as we watch it grow, it's a little bit slow here towards the end as time gets closer to 10. And then now let's start this one more time. Watch how quickly it grows at the beginning of this interval. That segment gets pretty long quite fast, and then after t gets to around 5, the length of that segment slows down quite some time. So what does that mean for us right now? It means that if we write that equation that gives us the distance of the line segment, that we can differentiate with respect to time, that we can take ddt of both sides of this equation, and we end up using some sort of like implicit differentiation to differentiate dx and y, because dx and y are functions of time. Therefore, they're really more not like variables, but like functions. D of x, or d of t actually, x of t, and y of t. So when we differentiate them, even though it looks like we're finding the derivative of a variable, what we're really doing is finding the derivative of a function. And the chain rule applies, which is why you see in the next line of work that when we multiplied by the derivative of the inside function, we took the derivative of x squared and it was 2x times dx dt. There's your implicit part. It's the chain rule part. And then 2y dy dt. And it turns out any equation involving two or more variables that are differentiable functions of time t can be used to write an equation that relates their corresponding rates. And it's the rates that are going to be of interest to us in this section. So here's our first example. Part A here, assume that the radius of a sphere is a differentiable function of t and let V be the volume of the sphere. Find an equation that relates dv dt and dr dt. So here's what we're imagining. We have a sphere. I'm going to try to make this a little bit 3D. And this would be the radius. Next, we want to find an equation that relates dv dt, that would be the rate of change in the volume, and dr dt, the rate of change in the radius. So first we need to begin with some sort of relationship equation or formula that relates V and R. And we know this for a sphere. The volume of a sphere is 4/3 pi r cubed. And what we can do from there is differentiate the volume, which is a function of t, with respect to time, and differentiate the right side of the equation, which involves r, radius, a function of t that changes with time, and then we go forward from here. What will that give us? Well, the derivative with respect to time of v is dv dt. Technically, I guess we could say it's 1 dv dt, but there's no need to write 1 times. On the right, 4/3 and pi are both constants, so we're just going to use the power rule on r cubed. The 3 is going to come to the front, act like a coefficient, multiply by 4/3, and we'll end up with 4 pi r squared dr dt. And there we have it. There's our equation that relates dv dt and dr dt. Let's go to part B. Assume that the radius r and height h of a cone are differentiable functions of t, and let v be the volume of the cone. Find an equation that relates dv dt, dr dt, and dh dt. So let's start with that cone. I'm going to draw a little diagram or picture here. Dash around the circular bottom. Here's the radius r, and then there's the height h. So we first need to start out with a formula or equation that relates the variables in question. That would be v, the volume, r, the radius, and h, the height. And we know this. The volume of a cone is 1/3 pi r squared h. You basically take a cylinder volume and then take 1/3 of that. So here's where we want to go. We want to next take the derivative with respect to time of both sides of this equation and see where that takes us. Well, ddt of v is simply dv dt. So we've got dv dt. On the right, since r is a function of time and h is a function of time, we're going to have to use a product rule because we have an r squared times h. It's like two variables being multiplied. In this case, those variables are really functions of time. So here we go with that. The 1/3 pi r squared we'll call the first function, h we'll call the second. So we're going to take the first function, 1/3 pi r squared, and then multiply by the derivative of the second. So the derivative with respect to t of h is simply just dh dt. It's more symbolic than anything else. We'll put a plus sign, continue on with the product rule, and then we have the second function h times the derivative of the first, and that'll be 2/3 pi r. And since we differentiated the r, and the r is kind of our inside function, like when we were doing implicit differentiation, multiply by dr dt. So we probably want to clean that up. We've got dv dt equals a 1/3 pi r squared dh dt plus a 2/3 pi r h dr dt. And there's our answer for part B. Next up is exercise 3 from your book. We worked that one in class. If we haven't yet, we'll save it for class, and that's where we'll stop this video.